Hello, everybody. Thanks for being here for the last session. So we've got a few more technical talks to round off today. The first one is Johannes Müller. I pronounced that correctly. So Johannes has been verifying CHERI where trust begins in hardware. He's a PhD student, researcher at RTL, and he develops 4 more techniques to verify CHERI processes at the RTL level, including functional correctness and timing side channels.
Thanks for the introduction.
Thank you.
All right, let me see you. Okay, perfect. So modern computer systems have a lot of security features in the hardware, and they build the foundation for the security of the entire system stack. And of course, CHERI is a very good example for this because CHERI offers a very sophisticated set of hardware security features. And of course, we want to make sure that this foundation is solid. That means we need hardware verification of the security features, and ideally, we want to guarantee to higher system layers that the security features are working correctly. Maybe we want to use formal verification for this. So CHERI has been submitted to formal verification in the past. So CHERI is intended as an ISA extension, and it comes with the SAIL model that we heard already a lot today about. And there have been properties on this, properties checked on this SAIL model. But the problem is, that if we can prove security on the ISA level, it doesn't necessarily mean that the processor implementing the ISA is also secure. And this bridge has been gapped by another line of work, we also heard about this morning, to prove the compliance between an RTL implementation of a CHERI processor and an ISA level SAIL model. This is a comprehensive and strong verification approach, but there are a few pitfalls to consider. And the first pitfall is that it is involved with high manual effort and high proof runtimes. At least that's what we took from the papers. And the second pitfall is that security vulnerabilities, there are security vulnerabilities that are only visible in the microarchitecture and not visible on the ISA level. And they are missed if you only do security verification on the ISA level. Okay, we address those issues with a somewhat orthogonal approach. So we do not start from a SAIL model. Instead, we formulate our security goals bit and cycle accurately, and then derive scalable properties from them and prove the properties directly on the RTL model. The benefits are that we can have exhaustive proofs with respect to our security goals and also cover those vulnerabilities in the microarchitecture. And we can derive really scalable proofs because we only focus on our security goals, not on complete compliance between the specification and a RTL implementation. We use this idea to write properties for one specific security goal, which is secure memory compartmentalization. So what is secure memory compartmentalization? How do we model it? So we start by modeling a processor and a memory, and we assume that on the processor there are tasks executing and a trusted entity like an operating system or a hypervisor that is in charge of securely switching between the tasks. And then we assume that there's an attacker task that is trying to break security among the tasks. Now, we define secure memory compartmentalization from the perspective of a specific task. And a specific task, for a specific task, the memory locations can be compartmentalized into the screen part, which is all memory locations where the current task has access to a capability that allows the access to this task, and to this red task where the current task does not have access to a capability that allows the access to this task. And now we can define secure memory compartmentalization as the conjunction of 2 sub-goals. So the first one is data confidentiality. It means that illegal reads from this red region, from the region where there's no capability allowing access, are not possible. And the other one is data integrity, basically the reverse, that it's not possible to write to those memory regions. There's one remark here. So in our task model, we only distinguish between two tasks in the capabilities that are available to this task. And this will become important on the next slide, because now we want to write security properties for secure memory compartmentalization. And we introduce a few macros. So the first set of macros is written in terms of the memory port signals. So read and write access are true if there is currently a read or write access, and data address is the address of this access. And the second set of macros is defined in terms of the capability locations in the processor or the memory. That means all buffers that can hold capabilities, all registers, and all memory locations where capabilities can be stored. And then we define two macros. The first one is task executing. It has task as an argument, and it basically means that the task and the argument is currently executing on a processor. And we can express this in terms of the capability because, remember from last slide, we only model the tasks by their capabilities. And the second one is this protected macro, which takes as an argument an address, which means that this address is not accessible with any of the capabilities available to the current task. Okay, now we can write properties for confidentiality and integrity, and they basically say if task T, so we write them for a specific task, if this task T is currently executing, it's not possible to make a read access to a protected data address. And for integrity, it's the reverse with a write access. Okay, now we have two properties, but for proving them on a real RTL design, two challenges remain. And the first challenge is that we define our capability, our properties for specific tasks. But what we actually want to prove is that any task possibly running on this processor is secure or cannot break memory compartmentalization. That means other tasks may look like this. So proving them or iterating over all tasks is obviously infeasible. What we do instead is we introduce a symbolic task with symbolic capabilities. And for this purpose, we introduce a new signal, which is a symbolic address, and we let the solver freely choose this address. So the solver decides to which memory location this address points to. And we also let the solver choose freely the capabilities that are available to this task. But we make one exception. So there's one constraint for the capabilities that this task has, and that is that the symbolic address must be protected. And because the symbolic address can be chosen freely by the solver, and the solver can also choose freely all of the capabilities that are available to the task, we are simultaneously considering all symbolic addresses and all capabilities, and therefore also all possible tasks in a single proof. Okay, that's the first solution to the first challenge. Now comes the second challenge, and that is how can we actually obtain properties that are both scalable and exhaustive with respect to our security goal. And here we use a property checking technique which is called interval properties. Interval properties define behavior over a finite time window, and instead of the time window starting at reset, we start at the symbolic start state. That means we are simultaneously considering all possible start states in one proof. You can imagine that this window slides over the entire time axis here. And then the design is unrolled to match the time window. Then we can use set-based property checking to check the property. And commercial tools are available that support this. For example, Jasper Gold by Cadence or OneSpin by Siemens EDA works with this type of property checking. And this gives us, of course, access to industrial grade and state-of-the-art solver technology. Okay. Now let's put the two solutions together and we formulate interval properties for our problem of secure memory compartmentalization, or to our two sub-goals of confidentiality and integrity. And this protected symbolic address macro basically says that the symbolic address is not accessible by any task, by any capability of the current task. And the property time window only spans 2 clock cycles, which is quite scalable, and the property basically expresses if the symbolic address is protected, it's not possible that there's a read access to this symbolic address. Okay, Now we have two scalable properties. Now the question is, are we done? Is this already everything we have to prove for secure memory compartmentalization? And the answer is almost, because our integrity property is fine, but our confidentiality property is a little bit too conservative. And to understand this, I will skip over this part, okay? And to understand this, consider the following scenario. This is, let's say, the processor attempts an illegal read from a protected memory region. That means in many implementations of processors, the access is not blocked outright, but the access is actually happening and an exception is triggered at the same time. But the exception takes a few clock cycles to be processed. And in the meantime, the illegally fetched data is actually propagating into the core, into some buffers. And this is okay, because this is not a security violation yet, because the task that is executing cannot read those buffers. This task can only, the current task can only read program visible registers, or how we call them, architecture registers. Then at some point, the exception kicks in and maybe clears some buffers, but and also prevents the further propagation. And a security violation would only occur if this propagation or if the protected data ends up in a register, in a program visible register, like the register file, for example. But let's say the exception prevents this, then we are almost secure. The only thing that can happen is that there maybe is a leftover, like a footprint in one of the buffers, and then future instruction execution depends on the data in this buffer. So over a so-called timing side channel, it can happen that information from this buffer ends up in a register file or in an architectural state variable. So for a confidentiality property that is not too conservative, we have to take this into account. And for this, we distinguish between architectural and microarchitecture state variables. So as I already said, architecture state variables are the program visible registers and buffers that are basically visible on the ISA level. And the microarchitecture state variables are all state holding elements in the processor. And how do we formulate such a property? We use a concept called non-interference. And in non-interference, we divide all state variables into high security locations and low security locations. And non-interference says that information from the high security locations must not influence the low security locations. We can formulate this in a two-safety approach. That means we take a second instance of the design and we assume that all low security locations are equal between the two instances. And we only allow differences between the two design instances in the high security locations. So this is how we model, in the high security locations, we model our protected data. Then we prove that from this point on, the low security locations remain the same. That means that the difference in the high security locations cannot propagate and influence the low security locations. We can also write an interval property for this. It's similar to the previous interval property. We also assume that the symbolic address is protected, and then we model the difference between the two designs by abstracting from memory. So we just say if there's a data access to the symbolic address, then there can be a difference, and if there's not any other access, there cannot be a difference introduced into the designs. Then we assume that the processor is in the same state in both instances, and we prove that the architecture state variables remain the same. Just in case you're familiar with our previous work on UPEC, this is a really similar property. If you haven't heard of UPEC, you can just forget this again. Perfect. We came up with a flow about this method, which is called CHERI. It looks quite scary, I think. I won't go into the details. I would rather like to talk about a case study we conducted on the CHERI IBEX processor. And there we found a few functional bugs, but we also found a side channel, which is not detectable by other methods. And here's how the side channel can be exploited in a potential transient execution attack. So an attacker would attempt to branch to an address outside of PCC bound. So the PCC is the program counter capability. It's a mechanism that governs from where you can fetch instructions and from where you are not allowed to fetch instructions. Okay, this is obviously an illegal instruction fetch, so an exception is raised. And then we detected that the exception execution is delayed depending on 2 specific bits of this fetch data. And then an attacker could, by measuring the overall execution time or by reading a performance counter, probe an arbitrary address in the memory for those 2 specific bits. Okay, this basically our properties, we use them in this case study, but we recently also put them on GitHub. So we published verification IPs for it. The verification IPs are basically property templates that are intended to be refined for a specific or for a new CHERI processor. And we also include the cookbook that gives guidance on how to refine it. And we also included 2 example refinements. And in case you are interested in why everything works like I now claimed, we also published a paper on ICCAT24 about this work. All right, thanks for your attention. Are there any questions?
Definitely got time for a few questions if there are any questions. Maybe I can ask the question. Just talking to a cube. Not at all strange. Just thinking about some of the security properties you got.
Yeah.
It's quite interesting that often, in many ways, you could see these as requirements for an implementation to satisfy. And yet, most of the requirements, as far as RISC-V International are concerned, is the ISA specification. And yet some of these properties will be sort of, if you like, beyond
exactly, yeah.
something you get in the regular ISA specification. So any thoughts on basically how do you think things should move on so that we can capture some of these key security properties and somehow incorporate them into, I mean, it's not an instruction, but into the ISA spec, into the architecture spec, so that we actually get secure implementations?
Yeah, so in my opinion, they shouldn't be part of the spec because if you start putting security properties like this into an ISA specification, you lose a lot of the freedom you have in implementing the ISA and optimizing your design to your specific needs. I think it should be something apart from the spec. So you should, I advocate for that you should do this type of security verification, but it shouldn't be required of you to implement your processor in a specific way that you satisfy those properties on an ISA level. And a lot of what makes them or what makes the property so effective is that they are cycle and bit accurate. So therefore, I think the ISA is really not the best spot for putting them. Yeah, I think you should. I mean, if a full formal verification is too expensive, then I think you should do simulation or do a verification you basically is affordable for the project, and only do the security on top, because I think at least for the small course, it's not that expensive.
Okay, thank you very much.
Thanks.
Has anybody else got a question? Super. Well, we'll thank the speaker.